is a distributed data parallel language, just like distributed data parallel. Okay, so it's a way that you can express distributed operations over data sets that are spread across a collection of machines. And this kind of data parallel basically means, and what we mean when we say data parallel is we're going to apply the same operations to different partitions of data that live on different physical machines or different nodes in some parallel compute infrastructure. If you think about a SQL system, it's essentially a distributed SQL query processor is also a data parallel system, right? We horizontally partition our data sets up, spread them across a bunch of machines, and we run the same operations on each of those data items, right? Okay, so in MapReduce, though, unlike in SQL, we only have two operations that we can apply on these distributed data sets. Not surprisingly, they are map and reduce, right? Okay, so what map does is it takes in one of these chunks of data that's living on a node and applies some mapping function to it. So what a mapping function does is it takes each element of a data set and it applies this function on it, which will produce a new element. So it's a way that we can transform or filter a data set in an element by element fashion. Okay? So map basically takes in a set of key value pairs and produces a new set of key value pairs and produces a new set of key value pairs. With this, it's K1, B1, pairs like this. This is K2, B2, something like that. Okay. What reduce does is it takes one of these data sets and reduces the really interesting one. What reduce does is it takes one of these data sets and for every item with the same key, it sends that item to the same physical machine. Okay, so it basically gives us a way to collect all the data items from one physical node, across our entire data set with the same key, and send it to the same physical node so that we can combine them together in some way, right? I'm just going to write co-locate items, same key. Okay, so the canonical example, right, we always see in MapReduce is this word count example. It's this goofy example, and I don't know why the Google people insisted on writing it in this even goofier way, but this is the example they give in the paper. So map takes in a string, and map takes in keys and values, okay? So again, these keys and values are distributed. Imagine a bunch of partitions of this data set that are spread across a bunch of machines. We're going to run map on each one of these partitions. The map function is going to get called once for every key at each one of these partitions. And what it's going to do is it's going to in the word count example, so we're trying to count the number of occurrences of each word in, say, a collection of documents here. In the word count example, what it's going to do is it's just going to emit the value 1, the key of the word and the value of 1 for each word in the input data set. Okay, so map just runs through the input document, splits it up into a bunch of words, and then for each word emits the value 1. Okay, so map is super simple. Right? And then the power of the reduce is that what reduce will, the framework itself, MapReduce, will take care of taking all the emits of the same word with the same key and sending them to the same physical node. Okay? And then the reduce will get called once for every occurrence of that key with a list of all the values for that key. Right? So in this particular case, the reduce is the values themselves actually don't matter, right? Because every value is the same thing. It's the string 1. What matters here is the length of the number of values, right? Because each node, there will be one invocation of the reduce function once per word that occurred in any document, and the number of values that thing receives will be the number of occurrences of that word. Okay, so the count for a given word is just the length of this values array. We just emit it directly. Okay? So in the end, what we get is an output, which is for each word the count of the result. I guess we could put emit key comma result. That would be more correct. Yeah.
Is there a difference between like the reduce? So like that reduce function does something specific, whereas like in general reduce co-locates items with the same key.
Yeah, okay, so remember, the way to think about this is what the programmer writes, and then what the infrastructure does for you is to co-locate the items with the same key. So the infrastructure takes care of taking the outputs of the maps, co-locating those outputs on the same physical node, okay? And then it calls this reduce function, which is what you specified here, the specific thing you want to do. So as a programmer using MapReduce, you write the map and the reduce functions, and the infrastructure takes care of the kind of movement of data for you. And actually the infrastructure, when you use Hadoop, which is the Java implementation of MapReduce, it has a bunch of stuff in it to do things like partition the data set up in the way that you want the data set split up amongst the input machines, and has a lot of other things you can specify besides just these two functions. But normally we talk about it as being these two functions of what the programmer wants. Yep.
Is there to do specific reason why you have to append one everything rather than like summing them up?
No, there's not really. I mean, so there are a couple of things. First of all, this is sort of the specification that's in the original MapReduce paper by the Google guys who weren't even using Hadoop. So I'm not really sure why they decided to go with this emitting one with every word. There's not really any reason to pass this key along. And of course, you could have done like a pre-reduction of this data in the sense that this map is processing some set of input documents. It could have reduced that set of input documents down. It could have pre-summed that set of input documents. That's a perfectly valid thing to do. And in fact, the Hadoop framework has support for this sort of map side pre-reduction of data. Like you can specify a function that gets run on the mappers that processes the output that can do this kind of pre-aggregation of the data if you want. Okay? Yep. Yeah, I mean, that's right. This thing has very little memory footprint. So, the pre-aggregation approach obviously would require you to keep a buffer of size of the number of words. So that, it's nice in that sense, right? I think this is just meant to be an illustrative example of a simple, something you could do with this framework. And it certainly illustrates the power of it because almost all of the work sort of in this is done by this reduce operation. The fact that the system co-locates these objects with the same key for you means that you don't have to do any work at all. It's sort of like for free, you just get everything you need to compute the file, right? Okay, so MapReduce it's become a sort of very powerful, widely used, widely known tool that a lot of people like because you can express these kinds of programs and the infrastructure will take care of parallelizing them for you. So let's just look a little bit at how this parallelization works to kind of remind ourselves what happens in MapReduce. So I just want to talk quickly about a few ideas. Okay, so one is distribution. Two is fault tolerance. And then three, we'll just briefly touch on the kind of layering, how MapReduce itself was architected, which is worth talking about. Okay. So the idea in the original MapReduce paper, they said, this is Google. So they said we're going to put all of our data into this Google file system. Remember we talked about the Google file system last time. In the Hadoop world, we replaced this with the Hadoop file system, so it's HDFS. But there's this distributed file system, which is the place that all the data lives in. Okay? And in the Hadoop implementation, they rely on this GFS file system for lots of kind of fault tolerance properties. So remember, GFS replicates every data item a few times. And so if one node goes down, then you can survive the failure of that node because every data object will be replicated, every file will be replicated in several places. Okay, so we're going to store the base data that MapReduce processes in GFS. We're also going to store the outputs of the MapReduce jobs back into GFS. Okay, so so now let's understand a little bit about how the distribution of this thing works. Okay, so what happens is that we've got a collection of worker nodes, okay, which are each going to read from GFS, a partition from GFS. Okay, so this might be worker 1, worker 2, worker 3. Okay, this file system, GFS is really, think of it as a distributed file system. So each worker has some storage on it that might contribute to GFS, but these workers may or may not be reading from their local disk. They're reading from some network file system. Okay, but they read these partitions, say P1, P2, and P3 of the input data set from their local data store. Okay, what they're going to do is they're going to apply the map function to each one of these inputs. Okay, and then the output of that map function is going to the keys that are in that output of the map function are going to cause the data to be we're going to redistribute the data according to the keys. Okay, so imagine we're going to take each output of each worker, we're going to hash its values, hash the key value, and that's going to tell us which reducer should receive that data. Okay, so this is just like hash partitioning in a distributed database system, right? So we look at the output key, in this case the word, we apply a hash function on the word that maps from word to the reducer node that is going to process this task, and then we just ship that output to that reducer node. Okay. In the MapReduce paper, they talk sometimes about, they say they use sorting. In HDFS, in Hadoop now, you can either use sorting or hashing in order to do this, kind of distribution. But anyway, we take each output key and we essentially map it to some of the workers. So these reduce workers, in the most general sense, are actually the same worker nodes as the map workers. Okay, so the map workers and the reduce workers are the same physical machines. It's just first they're processing map jobs and then they switch to processing reduce jobs. Okay, so this is the kind of reduce step. So again, you get something like this where every worker is sending work to every mapper is sending work to every reducer. Okay? And the system takes care of, it runs the partition, it runs each map job to completion on each one of the mappers. And then once all the mappers have completed, then it runs each one of the reducers. Okay? So a reducer isn't scheduled until all the mappers that it produces, that have produced its data, are ready to run. Does this make sense? Okay, so all right, so this is kind of the execution model, and then the last thing I just want to quickly talk about is the kind of fault tolerance model. Okay, so one of the things that the Hadoop, the MapReduce paper says is important is, so first of all, there's a couple of things about fault tolerance. So first of all, realize that these MapReduce jobs are often going to be composed into long sequences of multiple stages of MapReduce, right? So for example, even computing something like a join, right, might require us, a hash join might require us to do a couple of maps and reduces, right? Like we might have to, in the most general sense, if we're doing a repartition hash join, we might have to repartition both of the input data sets to be on the same key. So each of those would be a MapReduce job to do the right repartitioning, and then we would run another MapReduce job to actually compute the final join once the data sets have been partitioned on the right key attributes. Okay? So you might end up running 2 or 3 MapReduce jobs to do something simple like a join. And of course, in reality, if you're doing a big data processing task, you could easily imagine compiling 10 or 15 of these MapReduce jobs together. And I think they say in the original MapReduce paper that they were using MapReduce when it was first conceived to build the search index, and it was something like 20 MapReduce jobs to compute all the emergencies they need for building the search index in Google. Okay, so anyway, so we're going to compose a bunch of these MapReduce jobs together. So what happens is that this output of this reduce phase actually goes back into HDFS. Okay, so each intermediate step writes to each of these steps writes to HDFS, and then the next round reads the data back in from HDFS and does the processing. Okay, so all outputs go to HDFS, and then if you want to do something after that, you read it back from HDFS. Okay, the map and reduce jobs. What actually ends up happening is that the map writes to local storage on the mapper. Okay, and so this arrow here is not actually a transmission of data from between these 2 workers. It's a message from this worker that says, hey, I put the output that you need to read into this local file that you can go read and process. Okay, so there's a disk write at the output of every map. Okay, so the reason they do this is for fault tolerance purposes. Okay, so first of all, we want to save every intermediate result to HDFS because if one of these nodes crashes, one of these jobs fails, well, we have all the previous intermediate jobs that we've already computed into there, and we can go back and get the results. Okay. Furthermore, if one of these workers crashes somewhere along the way, right? Like a reducer is running and it crashes. Well, because the output of the mappers is in a local file, we can just go re-execute this reduce node, and it can just reread the outputs of these mappers without having to go recompute the whole MapReduce job in order to do that, right? And furthermore, if one of these mappers fails, well, it has its local storage on it, we can just rerun that map partition and then reschedule all the reducers that depend on that map partition without having to rerun all of the map jobs across the whole file system. Okay, so the fault tolerance model is basically we're going to use local storage plus HDFS to facilitate mid-query fault tolerance. And what I mean by mid-query fault tolerance is this idea that, again, you have to kind of put yourself in the Google mindset, right? So back in 2000, when the web was really big, computers weren't that fast, Google might have put a couple hundred machines working on this, and it might have taken them a day or two to actually build the whole search index, right? This is this big thing that they had to chew on for a long time. There's a non-trivial probability if you have a couple hundred machines or even a couple thousand machines, as Google, now they might be running clusters of tens of thousands of machines. In a day-long period, there's a non-trivial probability that one of those 100 machines will fail, right? Or much more than, a very non-trivial probability if you're running 10,000 machines for a day that one of them will fail, right? Because you figure on average, maybe you experience one hardware failure, I don't know, maybe once a year, given a typical machine will have a hardware fault, right? So you're going to have, or maybe once a month, you'll have a software crash that causes you to have to reboot. So if you have a reboot once a month, if you're running 100 machines, you're going to get for a day, you're going to have 3 reboots a day, right? If you have to restart the whole computation, it's going to take you a pretty long time to rerun that whole computation. So they felt that this kind of mid-query fault tolerance was really important, and so they architected this around extensive use of local storage in order to promote this kind of mid-query fault tolerance. This is something that database systems generally don't do. People generally don't worry about this kind of ability to cache mid-query results. Of course, you could decompose your database into a database query into a sequence of steps where you roast the outputs into temporary tables or something like that. But I think the reason people don't care about this is that typically people aren't running operations that take days to complete, and they typically aren't running on the hundreds to thousands of node-sized clusters that Google's talking about. Most distributed database machines run on 8 or 16 nodes. The very largest ones might run on 100 nodes. But it would be unusual to see database systems running on more than 100 nodes, unlike the sort of MapReduce case. All right, so this is the fault tolerance story. Obviously, it's probably pretty obvious that this fault tolerance story introduces some inefficiencies, right? We're writing all these intermediate results out. We can't pipeline anything. We're using the disk in between each one of these little operations. It's going to be pretty suboptimal. Okay, and indeed, if you go look at the systems, computer software systems literature in both the sort of operating systems, distributed systems world and the database world, Hadoop, showing that Hadoop performs terribly has become kind of a favorite pastime of all the performance-oriented papers. It's I built this system and it's X hundred times faster than Hadoop, right? And it's at this point, nobody really is all that impressed by you saying that because everybody knows and believes that Hadoop is pretty slow. And it's largely because of this kind of way that the basic framework was architected. And the Spark paper actually does a good job of breaking down a bunch of the overheads, and we'll talk about that in a little bit. All right, so there are questions. That's kind of all I wanted to say about MapReduce and Hadoop. Are there questions about it? Okay, so I just wanted to do this because I think it's useful and instructive to contrast the Hadoop kind of model of the world with the Spark model. Because I think they're trying to achieve a very similar kind of set of goals, right? They both are dealing with this kind of world where you've got some data, it's not really in a relational database yet, you haven't, you're not inserting it as, it may not be something that fits neatly into a very specific schema, and yet you want to do some data processing operation on it, and you want to do that data processing operation in parallel, okay? But the Spark model is somewhat different, and I think it's just sort of reflects the evolution of thinking after 10 years. The Spark paper was written basically 10 years after the MapReduce framework was first published. It sort of shows what people have come up with. So it has a bunch of ideas, some of which are borrowed from some existing new kind of, some systems that followed up on the MapReduce fork, and then this one kind of key new idea that it presents, which is this notion of a resilient distributed data set, which is their approach to implementing fault tolerance in a way that avoids these overheads of having to write all kinds of intermediate data out. Okay, so let's talk about Spark. Okay, so the programming model in Spark is this, I would call it sort of a data flow language. It's actually, in some ways, MapReduce can be thought of this, but MapReduce doesn't give you any explicit framework in which you can express multiple steps. If you're writing a MapReduce program that does multiple rounds of MapReduce, you just call the MapReduce engine multiple times from your single node program. In Spark, you write a single program that embodies a bunch of steps that you want to run over the data, one after the other, and they're all sort of programmed in this Spark programming language. So this is an idea that has been around for a very long time, the notion of data flow. The kind of most recent and popular implementations of it are systems like Pig, Dryad Link, are two other popular recent parallel programming languages that have been used to sort of build this. And I would say Spark doesn't really innovate in any way over what Pig and Dryad Link did. It's basically their own adaptation of this kind of a language and programming model.
Just because we moved on to Spark, what was the idea for layering?
What's that?
For layering, the third.
Oh, yeah, sorry. So I just wanted to say, again, this is an example of, I think, one thing that it's very similar to the idea that we talked about last week, where the Google guys just do a really, in the big table paper, right? The Google guys just do a really excellent job of reusing these components to achieve certain kinds of functionality, right? So here, they had this GFS system, and by layering on top of GFS, they get all kinds of properties that make it much easier to build Hadoop, right? Or MapReduce. They were able to sort of use it as a way to get distributed storage and reliable distributed storage, so you didn't have to think about how to re-implement that kind of reliability layer. They just got that for free from GFS, right? So they did the same thing in Bigtable. Sorry, I should have mentioned that. Okay, all right. So let's look at an example. This is just the example from the paper. There are actually 3 examples. Okay, so I can say things like lines is a distributed data set. Okay, so when I say lines equals Spark.text file HDFS, right? Actually, what I'm doing is I'm instantiating a data set object, which is the a distributed data set object. Okay, so this is something that even though I'm writing this as though it's a single centralized program, what I'm really doing is programming over a collection of data sets simultaneously. Okay, and then I can say errors is the subset of lines that contain the word error in them, or that start with the word error. Okay, and again, I create a new distributed data set when I do this that has been filtered to only contain the lines that have this error in them. Okay, and then I can say this thing errors.persist, and what this persist statement does basically is it makes errors visible as an object that other programs can execute against. So not just within my script, but people external to my script can reference this errors object now. Okay, and then I can do things like I can run functions like count. So I can count the number of errors, right? Or I can count the number of errors that contain the word MySQL, right? So I can say errors filter on all the ones that contain a particular word or term, and then I can count those, right? So I can compose these statements together in a very natural kind of programming language way, just in the way that we're all familiar with. And in fact, this is being executed as Scala objects. So Scala is the program itself. The programs themselves are written in Scala. Although if you go look at their the Spark page, they have bindings now for Java and Python and other things as well. Okay, and finally, I can do things, more complicated things, right? So I can, find the, so I can take all the time fields of all the errors mentioning HDFS, And basically, so what I do is I take this errors filter, I find the ones in HDFS, I split this up into 3 fields. Here they're assuming that the third field is the one that contains the timestamp, and then we collect all those timestamps together to get a list of all the unique timestamps. Okay? So again, you can write these operations that span multiple objects. I can do maps, I can do reduces, I can do joins, I can do filters, I can do counts, I can do all the kinds of things you might want to do. And you can see why this is kind of a nicer programming model than MapReduce, because although I can do maps and reduces, I don't have to sort of think about expressing everything as maps and reduces. It provides a number of higher level functions, including counts and joins and things like that would be, although possible to implement as map and reduce jobs, are not necessarily what, it's not obvious how you implement them as map and reduce jobs. You have to think a little bit to do it. And you have this nice ability to sort of define new distributed data sets based on the result of previous data sets without having to sort of explicitly create new objects in HDFS, or obviously create new objects in HDFS. Okay, other questions about the programming model? Okay, so operations, you can see a few of them here. I've already listed some of them off. There are things like map, filter, group by. So what group by in their notation does is it takes a list of key value pair, a set of key value pairs, and it maps it into a key and then a sequence of all the values that correspond to that key. So this is their notation. Okay, but this says you take all the occurrences of this key and the input, and what you get is a key and then a sequence that contains all the values that appeared with that key. Okay, whereas with reduce, you get to supply a reducing function that actually goes from this list of key value pairs to a reduced set of key value pairs, where each key only occurs once. Okay, so they also have a reduce that's much more like a MapReduce function where you actually supply the reduce function itself. With group by, you don't have to specify a function; it just accumulates into the sequence. They have joins and unions as well. Again, you can join 2 data sets where the key values are equal. You can take unions of 2 data sets. Okay, so all the kinds of set-oriented operations that you could do in a SQL database, they have sort of built into this thing. They're clearly, this depends on, of course, these all depend on the data set being sort of expressed as key value pairs. You need to load the data set in as a collection of keys in order to apply these things. So it's not obvious that these are key values, but in order to use these key value oriented operations, you have to use some reader that reads data that produces things in key value format. So they have a notion of just single objects that get read in, which are these lines, or you can have a reader which reads in key value pairs. Then you can apply these operations that apply on key value objects when you do that. Okay, so let's actually try and understand what's happening. Actually, maybe we'll take a 5-minute break. We'll come back at 3:12, and then we'll talk about how we actually implement this. Probably they don't, right? They're all over. Yeah, last year they were like in our yard on Thanksgiving. realize how big they are. I think it wasn't either. They're all over. They're probably all over. Usually I've seen here very close to the city. Not like in the area. It's kind of, I don't know why. I don't know if I've seen here, but I can't remember if I've seen it. I can't remember seeing it here, but very wild in the city. Maybe every staff overheads and lights, they're the best. No, not Santa Barbara. That might be wait, filter down. Yeah, what's that? We have four jobs. So that's but you know, it's like it's nuts. It's just pretty terrible. Oh, sure. Ocean. Because it's I kind of obviously do this thing. No, in fact, I think they use the high version. I mean, they might have added I don't know, they're kind of good. I don't think I mean, in fact, I think you have to sort of swing there's been more like disclaimers or construction yeah. Control that person so that I remember he did. All right, let's go ahead and get started, guys. So, uh-oh. See if I can get my notes back. It might be waiting. I think I can. I'll do my best. Okay, so let's talk about the implementation. All right, so the idea. Is we want to go from this programming model of this programming model, and we're going to do something sort of like what we did in MapReduce. So we're going to take our objects and we're going to partition them across, a bunch of nodes. So we're going to have this set of input data set of input data items, okay? And we're going to map these, we're going to apply functions that are going to produce new data items, right? So if I have this as this is a data set, imagine that contains 3 partitions, P1, P2, P3, okay? So this might be my, whatever it is, my errors, right? I can, apply something like a filter, and what that filter will produce is a collection of new partitions, again, P1, P2, P3, but that have been filtered, okay? So this is one kind of a, sort of, so in this particular case, there's sort of a mapping from of each partition to a new partition in the output, right? For other kinds of operations, though, you might have more complicated sorts of mappings. Let's see if I can grab it. All right, so for other kinds of operations, right, like if I've got a group by or something, right, then what a group by is going to do is it's going to need to take inputs, right, like P1 and P2, and it's going to need to generate new partitions that are the grouped partitions that contain the keys and values, right? So we're going to need to transform this P1 and P2 input into some new set of partitions, okay? And each one of these is going to contribute to these output partitions. Okay, so a group by will do something like this. Okay? So this kind of gives you so what the system has to do now, if you sort of think about the operations that it's going to perform, what it has to do is when I run a filter, it has to, for each one of these input partitions, run this filter job, right, to produce an output partition. Or similarly, when I run a group by, P3, it has to run for each input, it has to run the group by operation on its input, right? And then it has to save the partial results, and then run it on every other input, and then once it has all the partial results of that input, it can accumulate and build up the whole group that goes into each one of these new partitions, okay? And the way that this gets implemented is it's probably going to be quite a bit like the way MapReduce works. It's going to use sorting or hashing in order to map these keys to the input keys to the output partitions. They don't actually say how it's implemented in this paper, but you can pretty much infer that they're doing something like this. So they have implementations, and join, again, is going to do something similar, co-locate records that have the same join key in order to join the records together. Okay, so the key idea in this paper, and the thing that this paper spends the most time talking about, is this notion of, is how they implemented fault tolerance in Spark. So again, remember when we talked about we talked about in HDFS, the fault tolerance implementation is this, writing data to intermediate, writing out these intermediate result sets. They have a different way of doing this in Spark, which is based on these resilient data sets. And sort of the observation is that every one of these outputs here, right, depends deterministically on some input. Okay, so if we say that we'll never, if we agree to keep this input around, right, then we know that we can always generate this output by sort of recomputing it from this input, right? So if we don't overwrite this input, we can always sort of regenerate any output that we need, right? And so that means that if the system is cranking along, and we're going to have a sequence of these graphs that get composed together, right? As the system is sort of cranking along, if one of the nodes fails, right? As long as we've agreed that we keep all the intermediate result sets around, we can just rerun the computation that we need in order to recompute whatever data was on that output. Right?
How big are these partitions? Do we follow them in memory and do write them?
Okay, so again, so the system, that's sort of part of what they talk about in this paper is how do you manage these partitions. I think there's no requirement that these things fit into memory, although the use case that they envision is one where, in general, the kind of, and their big performance gains really are focused on the case where the data fits into the aggregate memory of the cluster. And that's probably a pretty reasonable assumption. You've got machines with 100 gigs of memory, you've got 100 of and that's a lot of data that you might fit into memory. It's not a requirement for the system, and we'll talk a little bit about how they deal with data sets that are larger than memory in a bit. Okay. All right, so fault tolerance is through this RDD, resilient distributed data set. Okay, so the idea is that you can recompute any object from its lineage, okay, and you can explicitly persist, say, on HDFS on a reliable storage system, some objects. So you get to decide which ones you want to persistently store. But in general, like in this case, this is maybe the input data set, right? It starts off on HDFS, so you've got that on HDFS. So you can always go back and recompute. You can always go back to HDFS, reread the data, and recompute it. Alternately, you can say, I want to explicitly store this output on disk so that I can kind of checkpoint it and come back to it and rerun from that. Okay. This RDD idea is also going to be the key to getting performance out of this system. Okay. So what we're going to say is that we can keep these RDDs between these intermediate processing steps. So performance is also these RDDs. Okay, and the reason is that we're going to cache RDDs in memory between steps. Okay, so these RDDs are serving a dual purpose. They're both allowing us to recover in the event of a failure because we keep this lineage information around. Where did this data set come from? As well as getting us performance because now instead of having to write each intermediate step out to HDFS in order to get recovery, we can just keep the intermediate steps in memory as much as possible and we'll get good performance, right? If we had to, if we don't have memory, and this is where this memory thing comes in, if we don't have memory to keep these RDDs in the memory of the system, we're going to have to write them out to disk as we process, and we're going to end up being kind of like MapReduce in that case because we're just going to have to write every intermediate result set out. Does it kind of make sense? So this abstraction gets us these two gains. One is the ability to cache things in memory, and the second is the ability to recompute kind of failed things. Okay, so let's look at it. Let's look at an example. So for this program here, this third program at the bottom, this is what this lineage graph would look like. Okay, so we just for each object, this lines object, we store the thing that we use to produce it. So the line, to go from lines to errors, we apply this filter. On starts with error. To go from errors to HDF errors, we apply this filter to find the ones that contain HDFS. To go from HDF errors to time fields, we apply this map to extract the third, to split the lines up into 3 fields and extract the third of those fields. Right? So all we have to do really is just remember this idea of RDDs means we just remember the input computation that we use to produce each RDD, and then we keep track of which RDDs are currently in memory and which ones aren't, and then we can sort of recompute any one of these RDDs that we want in order to run the data. And just to be clear, in this code here, the RDDs, the data sets, are these things like lines and errors. These are the RDDs that we're operating upon. Okay. Yep.
So with the recomputing, so it's any object. So you could have an RDD and only part of that data set was on a node that went down.
Yep.
And so because that graph kind of looks as though you might recompute an entire RDD, but in fact you.
Yeah, so let's talk about that's kind of what I want to talk about next. Okay, so here's like right. So the thing to think about is like, what is the nature of the dependencies between inputs and outputs, right? So you're right. This makes it look like you might compute the entire thing, but you don't necessarily have to, right? So if you're applying a map, for example, right? Remember, like in this example here, each partition or a filter, right? This partition, right, is on this is on machine 1, okay? This is on machine 2, and this is on machine 3, okay? And the system will actually keep track of, for each one of these partitions, which ones are, do you have available, which ones you don't. So if machine 3 goes down, well, then you lose, you might lose this partition and have to recompute it, right? But you don't have to recompute these other ones necessarily, all right? So this, okay, so the next thing to sort of talk about is this notion of lineage, right? And this shows different types of lineage, but these operators, right, they're not all this kind of linear relationship between input and output, right? Sometimes outputs, a given output gets fed into, a given output gets fed into multiple inputs, like when we're doing joins or group bys, right? We have this kind of many to many kind of mapping. And so we actually have to keep track of the fact that a given output partition can depend in general on an arbitrary number of input partitions, okay? So lineage is the dependency graph plus this computation is okay. And there are two types that they talk about. What do they call it? I'm now blanking on the word they use. Hold on. Call it like thin versus fat or something. What is it? Narrow and wide, is that right? Yeah, okay. So they have these two types. They talk about narrow and wide lineage, okay? So this is, for example, maps, and this is, e.g., group bys. Okay, so narrow lineage is this sort of, an input partition maps exactly to one output partition, and wide is like each input partition maps to, multiple output partitions, right? And this matters because, first of all, if you have narrow lineage, right, in order to do recovery, you only have to walk backwards a little bit, right? It also sort of is going to dictate their strategy for scheduling these kinds of operations. So we can kind of run a sequence of operations that only have narrow dependencies on each other, almost together like a single batch piece of work, right? So I can take 3 filters in a row and just apply them in a pipeline fashion, one after the other, right, to the input partitions. But as soon as I hit one of these kind of wide lineage things, it's kind of like a barrier in the computation, right? I have to stop, redistribute some stuff around, and then restart the computation. So I can kind of pipeline these, and then I have to kind of stall on these operations and do this redistribution. Does that make sense? Okay. All right, so hopefully we now have a pretty good sense of what is the kind of execution model like, how this RDD notion gets us both kind of performance and fault tolerance, and then how we can track this lineage through the operations. Okay, so the kind of key idea is really this idea of tracking lineage of operations and saving the computation that we need in order to regenerate some output. Now, we could, of course, do this. You could imagine doing this in a relational database as well, right? In some sense, materialized views or views are a way of capturing this notion of like a history of computation. But typically, people don't. Database systems don't have this kind of support for like recovery, automatically recovering a RDD when a failure happens, right? So I think that's kind of the sort of key idea here, right? And so they talk about this. So this is what I want to talk about next is this idea of scheduling and how they determine what to schedule when and what to recompute. So in particular, the sort of model with these RDDs is although they're cached in memory, you don't necessarily need to have, you're not going to have every one of these partitions in memory at all times, right? You can evict some of them from memory and then reload them, at later on an as-needed basis if you want. And the system takes care of, it automatically uses this lineage information to, kind of regenerate these things in memory when a failure happens or when you've done some eviction. So let's talk about those things now. So first we'll talk about scheduling, and then memory management. Okay. So the idea with scheduling is, well, what do we have to do? We have to figure out what task to run. Given a collection of inputs, given an operation we're performing like a map, what are all the different things that I need to run, and then two, where to run. Okay, so the thing to realize is that the sort of set of things that you can run. So first of all, the things that need to be run are, so this is an example from the paper. What they're trying to show in this is that black things are things that are cached in memory, and blue things are things that are not currently cached or available in memory. So we have this collection of partitions. If we want to compute this output G, right, then we can use the Lineage Craft to figure out each of the inputs that we need to recompute, right? So we don't need to recompute any of B because it's already available in memory, right? But we do need to recompute this thing that they've labeled as stage 2, okay? Because the blue things that are in F aren't available, right? Except for this one little part of E that is already cached for whatever reason. Okay, so we're going to need to recompute all of these things, right? So to recompute this first entry of F, well, I need to recompute this first entry of D, and then I need to recompute this first entry of C. Okay, the reason that they put all these things together into one stage is because they're saying this is an example of a group of operations that can all be pipelined together. Okay, so we're going to run sort of one sequence of operations that does this map, followed by whatever this line is that's not labeled, but is a union or a map or something, right? And then they're going to run this union, and all these things can kind of be done, each worker in this case, presumably this data set C is on some physical node. It will read that node in, it will reprocess it, produce this partition of D, we'll run that and produce this partition of F, right? So to compute this partition of F, we can just run that through on one node in a pipeline fashion. Okay, so this kind of gives us a notion of what tasks we should run next. We want to run that. We know in order to compute this output of G, which input tasks we have to run. Okay, so we're going to pick up one output of G, say let's run this thing, and then we're going to run all the jobs that correspond to this, that correspond to say this first partition of F. We'll regenerate this first partition of F, and then we'll move on to the second partition of F, and so on and so forth, right? So we have this set of things we have to schedule, and the scheduling task is kind of to choose what to run and in what order. Okay? So we use the Lineage Craft to figure out what to run. And they don't say really much about how they order the things to run. They suggest that basically the things you want to run are, once you've loaded the data into memory, you can run the computation on it, right? So like I can run D once, I can run this partition of D once this partition of C has been, loaded into memory. I can then go ahead and run this map job, right? And if it's not available in memory, then I can't run it, and I have to wait until that thing gets loaded into memory, until C gets loaded into memory before I can do it. That's basically all they say. And they reference some paper of theirs that talks about how you want to schedule this in a fair way so that you compute this as efficiently as possible. But I don't think they have anything really very deep to say about that. All right, so is you guys kind of clear on like what computation needs to be run? You just look at the Lineage Craft, you look at what's in memory, and you rerun it. In terms of where to run it, well, obviously you want to run things on the data, on the nodes that have the data in memory, right? So this partition of C is going to be loaded. This partition of C is going to be processed by some node. You want to then run the map to compute this partition of D on that node, right? You wouldn't want to run it on some other node if you could avoid doing it. So when you're doing these kind of wide operations, then there may be more discretion in terms of choosing what you should run where, like using information about what nodes are loaded or other things like that. Okay? Questions? Okay, cool. So we're almost done. I just want to talk quickly about memory management. So again, just remember that RDDs are cached in memory. We can evict them whenever we want. So what eviction policy does it probably make sense to use? Like what would you guys do if I said, so I suppose I want to compute, the whatever first partition of G, and I know I need to read in, this C, the first partition of C, the first partition of D, the first partition of F in order to do that. Suppose I don't have enough memory to load that for first partition of C. Well, what should I do? I'm gonna have to evict something, right? So what do I do? Yeah, you probably just do LRU, right? So that's what they say. They say we just do LRU, right? So you're gonna find the partition that was least recently used in the system on this node. You're gonna evict it in order to make room for this partition to sort of load this partition in and process it. Okay, so there's nothing real deep to say here. Just say use LRU. Okay, so really, in essence, I mean that's all there is to this paper. The key thing is this notion of lineage, and it gets them, some pretty substantial performance speedups. Before we look at performance, I'll just say one last note about, because there was this question about in-memory, what if data sets don't fit into memory? And it's a little bit hard to figure out exactly what's happening if, even one of these partitions doesn't fit into memory, but they sort of imply that they have, they have implementations of all their operators that should work, even in a in a case where you don't have memory to load a whole partition in. So they're using these secondary sort algorithms, or secondary, disk-based join algorithms that probably rely on sorting in order to do this, in order to do grouping and joins, right? So you can do group bys and joins by sorting, and then by using an external sort, and then processing things in sorted order without having to load the entirety of any of these things into memory, right? They don't explicitly say that, but that's kind of my assumption as to what they're doing. And they certainly explicitly say that they can support the case where things don't fit into memory, but they don't really expect that the performance of things that when it doesn't fit into memory, it's going to be very good. They're not claiming big performance gains. They're claiming they get their big performance gain when you can cache these kinds of intermediate results in a computation like this in memory. Because obviously, it's, if G can just run and read, B and F directly from memory, that'll be a lot better than having to, read the outputs of B and F from disk as you would have to do in a MapReduce kind of setting. Okay, so let's look at the performance. So this is one of the graphs from the paper. There are a bunch of graphs that look like this. They basically all show a 20x or more speed up on a variety of different computations versus Hadoop. So the graph here is sort of showing scaling. So first of all, we get linear scaling as the number of machines go up. That's pretty good. It also shows that they have these two implementations of Hadoop, one of which is the conventional implementation of Hadoop, and one of which is one where they force the data that Hadoop is processing to be serialized Java objects. So not as in the basic Hadoop where the Java objects themselves were read from CSV files. In the Hadoop in mem version, they were objects that were in the Java serialized representation and then stored in memory. Okay, so they actually, show, a huge speed up even against the version of Hadoop that caches intermediate results in memory. And they talk in the paper, actually, they have a nice kind of summary about why Hadoop is so bad, which maybe is entertaining to look at. The kinds of things they say are startup costs. So one of the problems with Hadoop is that every time you run a job, you start a new collection of JVMs. Okay, and they say that in this workload, like starting 100 JVMs on 100 machines and getting everything up and coordinated takes 25 seconds. Okay. What Spark does instead of starting a separate JVM, although Spark runs in the JVM as well, the notion in Spark is instead you already have the JVM started and you run, you start a thread for every job, and that has a much, much lower overhead. Okay, so it's like this is a stupid, obvious optimization that gets them, half of the, not half the speed up, but a quarter of the speed up or something that they fear. They also apparently HDFS is just a bad implementation. I mean, again, I said HDFS is kind of a punching bag, but the big overheads are they say there's huge overheads for going from HDFS, objects cached in memory of HDFS into the Hadoop system. So even though they're cached in Java representation, the system makes multiple copies of these things in order to load them in. So, but in general, the kind of takeaway, the kind of performance takeaways I think are performance. So the takeaways, there are these kind of little things that are annoying about Hadoop and HDFS, but the kind of big ones are, caching data, cache data between operations. That gets you a big win. No checkpoints. Between operations. So don't write all the intermediate data out between operations. Instead, use this notion of RDDs to be able to recompute things. And then the third one is that they try to schedule computation near data. So when they're running a operation, like one of these operations here, they'll run this filter on the same node that has P3 on it already in order to produce a new P3 on that node. So you don't go copy a bunch of stuff around the network. And in MapReduce, you end up doing this kind of copying stuff all around the network because you're relying on HDFS to sort of place the outputs of each stage, and you don't have very fine-grained control over how data is placed. HDFS does a little bit, tries to try and play some affinity games, but it's hard to get this right in the Hadoop world, and it's kind of explicitly baked into their model in this system. All right, you guys have questions? Yep.
The checkpoints could be useful if you have a long-running task and there's a good chance of failure.
Yeah, so I mean, of course, it is the case that if you have some giant pipeline of these things, and failures are really common, that you might need to go, that you could end up in this case where even if you can go recompute the inputs, you sort of have this problem that you might have faults all the time and you might never make progress, right? And so that's actually why you remember way back at the very beginning, it's still here, I erased it, but we said that they have this notion of you can choose which data sets you want to persist, and you can say these things to the disk. So they actually do have a notion of a checkpoint in this system, and it is essentially a hack for exactly the reason you're talking about. But I think what the recognition is, and I think this is an important recognition, is that that's not the common case in the way most people are using these cluster computing systems, right? Very few people actually are running jobs that run for days and on thousands of nodes, and very few people are likely to encounter a mid-query fault in reality, right? And so even if you do, you just restart it, and you're probably not going to need it. If you're Google and you're computing something over a crawl of the entire web, yeah, maybe you need it. And they have support for explicitly injecting those checkpoint operations into your workflow. So in your Spark program, you can request that a data set be persisted and written to disk as of, so you can take one of your RDDs and say, now stick this on the disk. Other questions? Yep.
So in MapReduce, we talked about keys and values.
Yeah.
Is that still true here, or are we talking about a more general?
They're sort of annoyingly silent about what their data model is. They say in a few places, and I think I mentioned this, they say in a few places that, I erased that part of my notes, but they say in a few places, like when I was writing out those operations, right? Some of the operations, like the reduce operations and the joins, explicitly require that the input be key value input. So it appears to me, without them actually saying this, that they basically have two types in their system. I mean, at some level they're using Scala and they have this entire Scala type system, but at the sort of level of distributed programming, they kind of have two types, like a blob of data and then a key value model. And in order to use these operations like the group by or reduce, you have to be operating on key value objects. Like you can't operate on these blob objects. Of course, one of the things that's happened in these distributed data set systems is that everybody, a natural thing to do is to look at this and say, boy, I could build a SQL processor really easily on top of this, right? And so this has happened in the case of MapReduce. People built this Hive system. These guys, the Spark guys, have a system called Shark, which is for Hive on Spark, which is again, once you have a system that can produce take a bunch of data flow like this, you can kind of bolt a SQL query like a SQL parser on top of it, and it's like you guys probably could all figure out how to build a query processor. Now that you've taken this class, like it's like you take the SQL query, you convert it into a plan, a set of filters and joins, and that's like that's your query, right? So people have done this, and that naturally makes sense. Yep. Yeah, they sort of say, oh yeah, it would be a really interesting thing to do to automatically figure out when to persist, but we don't. I mean, so it's a good question. Like, could you figure out when to persist? I mean, if you've been running, maybe you say, if I've been running for more than every n minutes, I should take a checkpoint. I should persist whatever objects I have, right?
From this lecture, it sounds like Spark is just better in every way than MapReduce. Is there any reason people would still use MapReduce over Spark?
I think probably not. I mean,
Legacy.
in fact, if you go look, it's like at least whatever the community is that cares about these things seems to have basically agreed that Spark is just MapReduce kind of done better. There are going to be some people who have made a big investment in Hadoop and they're going to keep using it, just like there are people who've made a big investment in Oracle and the system continuing to use it, right? But if you're starting new, there's probably not a great reason. I mean, the Hadoop ecosystem is richer, so there's probably it's a little bit more mature. It's been around for a lot longer. There's probably better support and better tools out there. But the Spark guys and the startup company they have is trying really, really hard. It's an open source project. They're trying really hard to get support, and all the big people who sell tools to support this HDFS, like the Hadoop ecosystem broadly defined, not Hadoop Hadoop MapReduce, but Hadoop like HDFS and everything else, are adding support for Spark so you can on their compute platform run Spark jobs instead of running Hadoop jobs. So I think it's not clear to me whether Hadoop is just going to morph into Spark or whether Spark is going to completely replace MapReduce. But to me, it's a better programming model than nicer. I mean, there's a bigger meta question maybe from this where you guys as you go out in the world, which is like, what's the relationship between SQL databases and systems like Spark? And there's a lot of debate about is one of these better than the other, right? I mean, I don't know that one is better than the other. Obviously, SQL is a high-level programming language that's great for expressing some kinds of things. Spark is somewhat lower level and probably somewhat more flexible and general purpose, and so you kind of have to decide what's right for your task. But anyway, hopefully you can see that a lot of what's happening in Spark, in fact, is built on ideas that essentially come out of the distributed database community. The way you build Spark is basically to build distributed implementations of operators like joins and reduces and all those other things that we spent the last few weeks studying. Okay.